Um, Mark and I have worked together for probably 17, 18 years, and ePLC, as it's known, is something that myself and Mark have been working on for 8, 9 years back in the day with Adept. And he will go through, what it is, how it's used, the fact that everybody on here are PLC people. I think once you see how it functions and works, it's pretty simplistic. Everybody on board is outside of V, Tina and Brad, both Rockwell / controller Compact Logics.
Yes.
Yes.
Okay. So this does function very, very well with Rockwell, Siemens, and recently with the acquisition of Adept through Omron with the NJ going forward. And probably because of the function block, it may seem a little simpler to others, but again, Mark and I have been doing this for 9 years, and we have hundreds of these out in the field. So Mark, I'm going to go ahead and leave it in your hands. How's that?
Sounds good. Well, thank you, everyone, for joining in today. As we go forward, if you have questions, please let me know. What I was going to try to do is just give a general overview of what the ePLC Connect is, kind of how it works, a little bit of detail. Now, when I say a little bit of detail, I'm really going to describe what you can do with it and the functions. Exactly how you do it is slightly different from Siemens to Compact or Control Logics to an NJ. But in all of them, the basic concepts are the same. How you tell it to move, those kind of things. It's the same basic concept. The bits may have a different tag name or a different function block, but the concept's exactly the same. So as we go through, if you got any questions, please just throw them out. It's the whole purpose of doing this is to give you the information you need and to make sure it makes sense to you. So before we start, are there any questions?
I don't think so.
Okay, excellent. So we'll just kind of jump in, I suppose. So one of the things, first of all, I suppose to say that we've seen is trying to understand in general why, in the first place, people are even going to use the ePLC Connect. I've been with Adept. I started with Adept in 1997, and so I've been doing this almost 20 years. And the entire time we did this, everybody's talked about ease of use. Ease of use. And in my mind, that's a bad term, frankly, because I don't think things are inherently easy to use per se. They're only easy to use based on your experience. The example I always use is if I give my iPhone to my 10-year-old daughter, does she know what to do with it? Of course, the answer is yes. If I give that same phone to my 88-year-old father, yeah, a little bit maybe, sort of he does, but not everything. So it's only easier for my daughter because she's familiar with it. She grew up with it, right? So years, I don't know, what was it, Dave? It was probably 9 or 10 years ago. We decided to try and come out with something that was, quote, easy to use, unquote, because it was something people were already familiar with. So we wanted to find something that people were already familiar with. And of course, every facility I've been to has someone who knows how to program a PLC to some extent. So we wanted to do this so that it gives people something they're already familiar with. I always joke that people are afraid of the robots. They're afraid of the machines. They watch Terminator too many times. But when I've done training classes, there's a perception that, oh my gosh, this is programming a robot, and this is going to be hard to do. Well, it's not. It's just you have to have someone show you. Well, the idea was, hey, if we do it in PLC, then we don't have to show people how to program because guess what? They already know how to program the PLC. So all we need to do is give them a little bit of background on kind of how it works and what bits they need to turn on, and then they can just run with it. And over the years, that has been our experience, that that we have not had a training class for ePLC. The training class has been me doing, at the time, older versions of this presentation. And then people get an example and they go with it. And it seems to go quite well. So again, the idea with the ePLC Connect is you do not have to know how to use our language or our programming environment. We have our own language, which is called V+. And we have the programming environment you use to get into that, which is called ACE. But the idea with the ePLC Connect is you don't need to mess with that at all. Pardon me. So all your programming is done in RS Logix or Step 7 or SysMax Studio. It's not something that looks like ladder logic. It is actually ladder logic in the programming environment that whichever of the three that you prefer to use. So the other thing that is nice is that because the programming, the sequencing of the robot is done on the PLC side, you're not relying on having to back up from multiple different locations. The PLC backup has all your stuff in it. And because of that, then of course, there's no real adept language-centric stuff you need to know. You just have to know how in general it works and how to program the PLC, which you already know. The other thing to point out is that it works with a variety of robots. It's not keyed to one type of robot. So it will work with the different types of robots that we have. It's a robot. It's an external device, and you tell it to move, and it'll move. PLC-wise, I kind of already mentioned this, but we're going to communicate either over TCP/IP or Ethernet IP, just depending, with Omron, with Rockwell, and with Siemens. The nice thing is that because of this architecture, the cabling and everything is greatly simplified. So for the ePLC Connect, you're not generally going to have an external controller. I mean, you certainly can if you wish, but in most cases, people don't even have an external controller. They use the controller, which is built into the base of the arm. So from the cabling standpoint, you're going to plug your 24 volts into the back of the robot and into your PLC. You're going to have an Ethernet connection, which connects the robot to the PLC. There's an Ethernet port on the amplifier in the base of the robot. So you just plug the Ethernet cable right into the robot. You're going to give it your 210, 220 AC, and then you plug your safety stuff in. And then if you have multiple robots, you have the robots and you provide 24 volts, you provide your 220, you tie your safety in, and then you just have a switch on your system, Ethernet switch in your system, and plug all the robots in. And a single PLC can then talk to multiple robots. Each robot, of course, would have its own IP address. Now, one thing I want to make clear as we're going through this. I've mentioned it, but I want to make sure you understand what it means. When I said use the PLC to sequence the robot, in no case are you using the servo control, the motion control capability of a PLC to run the robot. That's not how this works. Our operating system is still running on the robot, and it's still using our servo control and our amp to run the robot. In the background, really all that's happening is you're passing data back and forth between the PLC and the robot. So the PLC is using either Ethernet IP or TCP/IP to pass data back and forth to the amplifier. The amplifier has the controller built in, and it's telling the robot what to do. And then there's status information, of course. You have commands, so you have to have status, and then that's passed back to the PLC. So we're doing the servo control. We're making the robot move with our controls. The PLC is just telling it what to do, which go here, do this. So does that make good sense so far?
Yeah, that's making sense.
Yeah.
Great, thank you. So the next thing I kind of wanted to talk about is which applications do we see customers using ePLC Connect for? Frankly, it's almost easier to go to the next slide and say which, or better just to use our standard V+ language for. People use it for pick and place and machine tending and loading pallets and unloading pallets and loading machines and unloading machines, screw driving, just standard pick and place in a normal application, right? That being said, if we look at applications that are oftentimes better suited for V+, conveyor tracking, real high-speed applications, and complex. Now, let me explain what I mean by this, okay? So for conveyor tracking, the Rockwell implementation does not have any provisions for doing conveyor tracking with PLC control. So you're not going to use ePLC Connect with conveyor tracking with Rockwell or with Siemens. We did just come out with that for the NJ, but it has not been released for Rockwell or Siemens. High-speed applications. So what do I mean there? Well, we've had customers who've done high-speed applications, for example, with a Quattro robot, picking and placing at 115 a minute with ePLC Connect. So why do I list this as jobs that are perhaps better suited for just plain old V+? Because we want to make sure you're happy and that it's going to do what you expect it to do. So we want to at least talk to you about it and make sure it'll work if it is a high-speed application. So what I mean is, if you're doing an application where you're doing a lot of very, very short moves, for example, with the Quattro robot, the challenge is you need to make sure that the communication is fast enough to and from the robot so that the robot isn't starting to decelerate before it gets the next command. So if you're commanding it, let's say a Quattro to move in like 1 millimeter increments, that is not, at very high speed, that's not a good PLC Connect job, all right? So we just want to talk to you about it. Oftentimes, people use Hornets, people use Quattros with ePLC Connect, the very high-speed robots, and that works great. But we just want to make sure that it suits your actual application. So we want to have a conversation about it. We want you to be happy. So, complex applications. One of those may qualify as like a dispensing application, where you are doing you need to squirt sealant or whatever it may be with the robot. Now, we still have a lot of people that do this exact application, dispensing sealant or gasket material or whatever with the robot using ePLC Connect. So again, why is it on this list? There can be some gotchas. And again, we want to make sure you're happy and that it does what you want and expect it to do. We want to discuss it up front and make sure it'll do what you want. If you have an application where the tool tip speed is imperative to the, let's say, the quality of a polishing application or something, right? Well, then maybe that's not a good ePLC job. But if you're just squirting some sealant or gasket material into a channel, well, that's probably a great fit. So again, I'm not trying to scare you off, simply and only trying to make sure that for some applications, we talk about it ahead of time. So the next thing I want to talk about is some of the features that are included. So you can have multiple robots running on one PLC. You saw that slide earlier with like the 6 robots. You can certainly do that. Each one would have its own IP address, and so that's generally not a problem at all. Stop on digital input. What this means is if you have an application, let's say you have a sensor. We had a customer that was picking up solar cells. And they didn't actually know how high the stack was going to be every time, because an operator made a stack of them and put them in the machine, right? So maybe there was, 42, maybe there was 45. So what they did is on the very first cell, when they loaded the machine, they would come down very slowly. And as soon as the vacuum switch made, they wanted to stop the robot. So that's an option that we have, and that's what the stop on digital input means. So then there's also MCP programming, manual control pendant. That is an option that you can get with your robot. That's an external pendant. Generally, people use it for just kind of jogging the robot around, teaching points. You do not use it for programming, just for jogging and, again, teaching some points. But if you wish, there is a display on it that you can write to. So if you wish, you can come up with a very simple, like opera menu on the pendant, if you wish. You would program that in, of course, but there's functionality in the ePLC Connect to allow you to do that. The latch function is, if you did that stop on digital input, which was number 2 on this list, right? I found that the top of that stack of solar cells. Well, the latch function just simply says, hey, where was I when I saw that latch? Because you probably need to know where the top of the stack is so that you can then go to the next one and the next one and the next one further down, right? There's a break, which means you can stop a motion if you're in the middle of a motion. The state function gives you a lot of information back. That's kind of status information back from the robot as to what it's doing. The align function is very handy if you have a 6-axis robot, then you need to make sure that the tool flange is lined up with like the mounting surface or something. You can use a tool offset. Are you all familiar with the idea of a tool offset?
Yeah, I think I understand.
Okay, good. I mean, it's basically, instead of keeping track of the center of the mounting flange, you tell the system that you have an offset tool and you want it to keep track of that other point instead. So you can do that with ePLC Connect. You can create palettes, which of course it may be important depending on your application. You can do arcs or circles, and you can use vision with it as well if you wish. So then, of course, we do have documentation that is available online, and if you have any difficulty getting to it, we can certainly point you to it. We're happy to help with that. So the next thing that I wanted to talk about then is some of the data that we pass back and forth. You kind of break it down into commands and into states, which hopefully makes sense. The commands are, hey, robot, you need to go do this. And here's how I want you to do this. I want you to move here at this speed, at this acceleration and this deceleration, or go to this pallet in this position on the pallet, or whatever it may be, right? So the commands are telling the robot what you want it to do. So we have registers, and again, and there's a data structure which represents the commands that you're going to give the robot. How that is represented is slightly different from an NJ to compact logics or control logics to cymatic controller, but at the end of the day, the concepts are identical, right? So there's going to be on any of the systems, doesn't matter, there's a command to turn on high power to the robot. Or there's a command to stop on input, as we discussed, or to break, or to read the position that input turned on at. You can reset faults. You can calibrate the robot. And when I say calibrate the robot, I mean we have absolute encoders on it. But when you cycle power to the system, you drop 24 volts to the amplifier. After you do that, you have to calibrate the robot, which is simply issue the calibrate command, and then it'll read the encoders and make sure it knows where it is, and that's it. It doesn't move or anything like that. If you wish, there's to use it, there's a jog command. So the whole idea of the jog command is if you want to make let's say you've got a panel view or something, and you want to make a virtual robot control panel to move the robot around, you can do that. There's a jog command, which would behave like hitting a jog button on your manual control pendant, but you can do that from the PLC too, right? So you can make your own little virtual jog pendant or something on a panel view if you wish. There's an align command, and again I said that's where you snap the mounting flange parallel to one of the world frames, like the base, the mounting plate or the table that you've mounted the robot on. And then one of the ones that you're going to probably use the most frequently, besides enable on power, probably one you're going to use absolutely the most is the move command, right? And guess what? There's, of course, some qualifiers that you need to provide to tell it how to move. But there's a bit to tell it to move. So you set your qualifiers and stuff, you turn on the move bit, and the robot will go. We have a jump command. The whole idea of that is to take wherever you happen to be, to go up some number of millimeters, go over to a point, and then go down that same number of millimeters. So it's up, over, and down. And the goal of that's simply to try to make the programming perhaps a little easier for you. We have arc and circle commands. So if you want to move the robot tool flange in an arc or in a circle, you can do that easily. You can define locations, you can define pallets, and you can invoke tools. So these are the commands, the instruction set that you have available. I mentioned that there's the jog command, which kind of turns the robot into or allows you, pardon me, to turn the panel view or some other display that you perhaps have into a touch screen jog pendant for the robot if you don't have the actual pendant. So there's a whole set of jog commands just for that. You, of course, have access to the inputs or the outputs of the robot. And then we have some motion qualifiers. And the whole idea with the motion qualifiers is you've told the robot to go to a point, and you need to tell it how to get to that point. So do you want it to move in a straight line, or do you want it to move in an arc? Do you want it to go to an absolute point in space, or perhaps you would like it to move relative to its current position? You may want to tell it to stop when it gets to the end point, or perhaps you want it to move through the end point. And if you want it to stop, how close does it need to get to that point? And then you may need to specify whether the arm is a right and righty or lefty configuration. And if you have a 6-axis arm, you also need to specify flip, no flip, and above, below. Then we have in addition to the motion qualifiers, we have parameters. So you need to tell it how fast it's supposed to go on the way, and what acceleration and deceleration you would like to use. What approach and depart height you're going to use, the location it's going to go to, if you're using a pallet, which pallet you want to go to. Again, if you're using a pallet, which particular point on the pallet you want to use. And then there's an actual location register. And the location register, the idea of that is, that's the coordinates of the point you want it to move to. There's also commands to define the pallet, which we'll talk about here in a little bit. And again, there's some commands to communicate with the pendant, which if you're interested, we can talk about kind of when we finish up the main presentation. So again, these are part of the data structure that we put together for the ePLC. And the idea is, again, whichever platform you're using on the PLC side, this general functionality is going to be the same. So these are the commands. These are the things you're telling the robot to do. Then we also, of course, have to have some status. So you told the robot to go do something, but did it do it? So if you think about it, we had on your command side, turn on high power, or stop on input, or reset a fault, or calibrate the robot, or move, right? So there's these types of commands. So on the status side, we usually have kind of a partner for the commands. So you can tell the robot to turn on high power, or one of the status registers that's passed back is high power to the robot turned on or not? Is there a fault? You can clear a fault, but is there a fault that you need to clear? Is the system initialized? Is there an emergency stop? Are we running a command? Is the robot in position, or is it currently still moving? Did you get a latch? Are you jogging the robot with those jog commands? Did you invoke a tool? is the robot in righty or lefty configuration. There's also a system heartbeat, which is basically passing back and forth, so we know that communication has not dropped out between the robot and the PLC. For certain things, which we'll talk about in a bit, you may use ACE in conjunction with the ePLC, but that's only if you're doing vision. And if you are doing that, then you need to actually know that ACE is connected and trying to do something. So there's a bit for that. And then there's some state information and motion counter. So you know if the robot started a new motion, is it currently moving, how far is it away from the destination, those types of things. In addition to those, we're also going to pass back any error information. So if you have an e-stop, for example, you'll get a bit that says that there is an error, that's the fault state. But then in addition to that, you actually get an error message saying that there's an e-stop. So having a bit say there's a fault is fine and dandy, but it doesn't help you all that much if you don't know what the fault is, right? So we include that as well, is that both the code as well as the message, the text string, which says what the problem is, and we pass that back as well. If you're using dependent, it returns some feedback from the buttons on the pendant. One of the things that we also pass back as status is, where is the robot right now? The robot position, the current position. Because of course that's often very important to know. And then if you are using vision, if you're using the ACE site vision with the robot, the ePLC Connect, which you can do, of course, then there's some status information and some commands that go with the vision portion of it. Basically, hey, run a vision sequence. Did we get results? How many did we find? Those types of things. So if you look at them, this is just some detail on the command bits, but I want to point one thing out. Again, those commands that we talked about: turn on high power, stop an input, read a latch, jump, move, align, jog, do a circle, define. We do have some limitation on which ones can be on at the same time. So you cannot tell the robot to move and to jog at the same time. You know, that's not safe. So the ones with the yellow dot here are limited such that only one of those can be on at any one time. But of course, if you accidentally violate that, it will throw a fault. And then the status bit that says there's a fault will turn on. And the message string that we pass back will say only one command bit can be on at the time. So it'll tell you very clearly what the problem is. So a little more detail on the motion qualifiers. When you're moving from point A to point B, you can tell the system, again, how you want it to get there, what the motion should be like. So are we going to use Cartesian or joint coordinates for the position? You know, what is the position? Are we going to go in a straight line? Are we going to go in a curved motion? Are we going to go relative to the current position, or do you want it to be an absolute coordinate in space? Should we move through points, or do you want us to stop at every point? If you want us to stop, how close do we need to get? Should we do just plus or minus 180 degrees? Or should we use plus or minus 360 degrees of rotation on the theta rotation for the robot? And then what does the robot look like, righty, lefty? And we'll get to that in a minute with the graphic that makes it on the next slide here. It makes it hopefully a little easier to see. So if you have a scare arm, it's usually pretty obvious which configuration it's in. For a 6-axis, you know, for an articulated arm, one of the Viper series of arms, it's frankly, for me, I oftentimes have a hard time remembering which one's which. So the status bit that tells you which configuration it is in makes it very easy to simply record that and then use it when you're telling the robot to move. On the motion parameter side of things, again, we get to control the speed, the accel, the decel, and the profile. Are you all familiar with the acceleration profiles? Basically, the jerk parameter.
I'm not real familiar with it, but
Okay. So the graphic here tries to just give a real simple illustration. Basically, if you've ever been on an elevator, and when the elevator starts up, you bounce, like it makes you bounce, you know?
mm-hmm.
Either, you know, you bounce down when it starts up and you kind of, you know, bounce down and then you rock on your knees a little bit. That's because they didn't use an S-curve. They had a trapezoidal profile. So trapezoidal has rough corners, right? These kind of sharp corners, which says just start accelerating. But a profile of something other than 0 on our system actually smooths out these corners so that you get a smoother motion when you're moving the robot. That can be very helpful if you're using Quattros or Hornets. You're going to use those pretty much all the time. But if you have even, let's say, a Cobra robot, one of the Scara-style robots, but you have a heavy payload or you just need to move very smoothly, perhaps it's a lab automation job and you're handling vials of liquid or something, and you want to go fast, but you need to move smoothly so that you don't slosh all the liquid out of the test tube, right?
Mm-hmm.
Then you can use that profile, the S-curve, to smooth out the motion. Does that make okay sense?
Yeah, that is. Yep.
Okay. And of course, you can also specify the approach height, you know. And again, if you think about a standard pick and place cycle, you're going to oftentimes, if you have something in a pallet, for example, or a carton or box, you're going to come in above it at some approach height. Then you're going to go straight down and grab the product, and then you're going to come back up and then move somewhere else so that you don't hit the box or the pallet or whatever you're picking and placing from, right? So the approach height is, you can specify, there's a register for that. And then, of course, one of the most basic ones is the location, like where am I going to pick and place the stuff? Now, there's 2 ways to do this. One is to use a location number, and one is just to use the coordinates, your X, Y, Z, yaw, pitch, and roll coordinates that you're moving to. The rationale, the reason that we have this is, you know, we've had the ePLC Connect for a bunch of years, right? So when we came out with this, we were the first ones to bring it to market, but when we came out with it, the implementation, Ethernet IP was just coming out. So we actually did it in serial DF1. Well, the serial communication was not quite as fast. So because of that, we actually got to the point where the robot was fast. The robots were fast enough that they were done moving before you could send more data to tell them where to go. You can still have that problem sometimes if you do very, very short moves on a coordinate and real high speeds. But for Cobra, generally, it's not an issue anymore. But again, when we started out, it was a problem. So we said, hey, guess what? It's a lot easier to send a single integer like 72, go to 0.72, and then to send X, Y, Z, yaw, pitch, and roll, which are all real values because there's a lot more data there, right? So when we started out way back when, we said, hey, guess what? The programmer is going to have the system set up so that it downloads all the points. And here's 0.1, and you define it. And here's 0.2, and you define that, and 0.3, and you define that. So basically, it sent it over to kind of just RAM memory, temporary storage on the robot side, and volatile memory. And then you would simply later on say, go to this point. Well, that worked out really well because if it took an extra 2 seconds when you started the machine up, no one's probably going to notice, right? But if it takes an extra 100 milliseconds every single move you do, that might be an actual problem. So the idea was to try to simplify matters, to speed them up. We'll have these numbers. Well, nowadays, with the Ethernet IP communication, it's not really as big a deal, again, except in very specific circumstances. So because of that, the idea is, hey, if you were going to still use this structure that we set up so that when you define a pallet, if you want to define a pallet, you're going to define some points and give them numbers, and you'll use the location numbers to define your pallet. We'll talk about that a little bit more here in a bit. So those are the motion parameters. So we talked about a lot of these parameters and stuff. How do you actually make the robot move? So you give it a speed, an accel, a decel, and an acceleration profile. And then you give it a location to move to and tell it what kind of location it is. And then you turn on the motion qualifier bits. Is it a straight line motion? Is it a relative motion? You make sure that the location number is 0, because usually people don't use that anymore except with pallets, right? And then you turn on the move bit. So you gave it a point to move to. You told it how to get there, your speeds and qualifiers and straight line or whatever. You turn on the move bit and it goes. Then once it starts moving, you can give it another command, or you can just wait for it to stop, whichever you prefer. And that's it. So, I mean, I know I've been talking about a lot of these parameters and stuff that we have, but if you have ever done robot motion before, hopefully this is all pretty standard and hopefully very familiar for you. But then the idea is you stick some values in some registers and you turn on a bit and the robot goes. So then if you're going to use a pallet, or if you just want to, in reality, just save off your points. When you want to teach a location, teaching a location is really done completely on the PLC side of things, right? So teaching a location is moving the robot somewhere in space, either like with a real pendant or with a virtual jog or however you choose to teach it, right? And then you look at the status information that shows the robot's current position. And you then save it in a register, whichever register you want. Now, of course, our example code has registers for that. But you can use your own if you want. You don't have to use ours. So you grab those values from the status, where is the robot right now, the current location, and you stick them somewhere and you save them. Like that's it. That's saving your locations. If you're going to download locations, again, if you're going to do a pallet and you need to send those points over to the robot, then you can certainly do that as well. So then you give it, say, okay, hey, this is location number 1, and here's my XYZ off pitch and roll, and you turn on the define location bit. Wait for it to be done, turn the bit off. And that's it. So one thing I do want to make note of, when you're looking at locations on our system, you can either specify them as joint values or a Cartesian value. Are you all familiar with the difference? Do you guys know what that means? Is that what that means?
Yeah, I understand that.
Okay. Okay. Tina, you good with that as well?
Yeah, I'm good.
Okay. I don't want to bore you. I figured you did, but I want to make sure I didn't want to gloss over something. The one thing to point out, and I think a lot of other robot manufacturers do it in a similar fashion, but our XYZ yaw pitch and roll, the yaw pitch and roll it is a Euler angle, so it's ZYZ. So it's not the same yaw pitch and roll you have with like an airplane, right? But when you're working with the system, it'll become pretty apparent pretty quickly. So if you decide to do a pallet, we wanted to try and make it hopefully as easy as we can for you. So you needed to define and download 3 points. You give it a starting position, a position in the first row, and a position in the last row. And then you tell it basically how many rows and columns you have. And then it just does the math and figures out the spacing for you. The one thing that you do need to give it, there are a couple things, I apologize, not one, but a couple things you need to give it is you need to tell it what kind of a pallet it is. As you see here, it can be a perfectly kind of a square pallet, or you can have offset rows, and there's a bunch of different ways to do offset rows, right? So we tried to be as comprehensive as we could and give you some different ways of doing. There's actually a few others I think that are not shown on this slide, but they're in the manual. So you can have a bunch of different types of pallet configuration. And then you can also specify how you want to move through the pallet. You kind of see here at traversal direction 0, it's kind of the typewriter style, right? You go 1 to 5, all the way back to the beginning. 6 to 10, all the way back to the beginning, right? So you're always going, left to right and starting a new row. The other way is kind of, I don't know, I call it snake style, I guess, where you kind of go over and then up, and then left and up and right and up and left and up, and so that is totally up to you. That's your preference. So that's the pallet. So if you want to define a pallet, basically you teach your points that we just mentioned, those 3 points, basically your corner points, right? You give it a pallet number. Hey, this is pallet number 1, and you give it the 3 points, and you define the pallet, and you wait for the command executing bit to go high, turn it off, and wait for it basically to say that it's done, and that's it. So again, defining it is just sticking some values into registers and turn on a bit, waiting for it to be done, turn it off, and you're good to go. Similarly, if you want to use the jog functionality that we discussed, again, enabling you to not necessarily program, but you're going to have somebody maybe hold down a button on a panel, and that will function as a jog pendant for the robot. We have the bits to allow you to do that, and you can jog the robot in multiple modes, world mode or tool mode or joint mode. And then, of course, if you're doing that, you need to tell it which joint or which direction you want to move it. Then you turn on the jog bit, and it'll go. So I know that we went through a fair amount of information fairly quickly, but my goal is to at least go through and give you a general idea of kind of how it works, and then see what other questions perhaps that you may have. So, do you have any other questions? Is there anything you'd like more detail on? Does it make good sense? What do you think?
I have a couple questions about the move parameters is what you named them.
The motion parameters, yeah.
The motion parameters. So the approach height parameter is a real number, you said? So what does that translate? Is that into millimeters then?
That is in millimeters, correct.
So, and then with that approach height, if I have that set to 20 millimeters, and then tell the robot to move to a point, it would go up 20 millimeters, move to that point, and then go down 20 millimeters as well.
It would do that if you use the jump command, the one shown here, the command _jump. The move command that just does kind of one segment at a time. So for example, because you may not always want to do a jump, right? You may not always want to go up and over and down. Maybe you just want to go to a point in space, right? So the move command, so if you have a point in space and you want to do just a move, you would have your approach height set to 0, and then you'd set your speeds, accels, decels, all that stuff, and you tell it to move, and it'll go to that point. But if you do that exact same thing, but instead put a value of, let's say, 50 for the approach, then it would come in 50 millimeters above and go down. So then the third scenario, instead of using the command move, you used the command jump. and you put 50 millimeters in. Then what it'll do is wherever you are, it'll go up 50 millimeters. It'll then go over your target point you told it to go to. It'll be above that by 50 millimeters, and then it will come down. So
Okay, so
we try to give you some flexibility.
Yeah. So with the jump command, you set that 50 millimeters by using the approach height parameter, or you set that?
Yep.
Okay, that is the parameter that you use to set the jump height?
Correct.
Okay.
Yeah, the jump command is frankly, is a little more restrictive in that it's, you have to have the same height at both ends. But the intention was not necessarily to provide a huge breadth of variation in it. It was trying to provide hopefully a simple command, just to make it a little easier for people. And it comes in handy, you know, again, like if you're doing a high-speed application with the Quattro, then when we came out with it again way back, when the serial DF1 communication, that was very helpful because it reduced the amount of communication back and forth. So it's just trying to simplify the process.
Okay.
So any other questions?
So when you're setting like the robot's position, you have like a bit to put it in like free mode where you can move it by hand. And then will it
robot, correct?
Yeah.
So,
and then will it tell you the position that it's at?
Yeah, sure. So there is one of the status registers is the robot position. So to give you the actual world position, which is Cartesian coordinates, it'll give you the actual joint position, which is your joint 1, joint 2, joint 3, joint 4, joint 5, and maybe joint 6 positions. The one thing to point out though on that, so you do have on the commands, you do have, you can put it into free mode and jog. However, that is not functional for all the robots. Because if you have an articulated arm, right, and one of these guys, and you accidentally freed up joint 2, the arm's just gonna kind of flop over, right, and probably break stuff. So we do prevent you from doing that on some of the robots. You can do it for Cobras. Actually, I believe Cobra is the only one you can actually do it on, because it doesn't really make a lot of sense to free up the joints on a Quattro or Hornet one at a time, because they all have to move together. So, the other thing too, of course, is depending on the robot, there's a brake release button. It just depends where on the robot it is or how it works. So on a Cobra robot, it's on the let's see if I can find my picture here. On the Cobra robot, you see here where there's the display right on the front and kind of in the middle in the front of this top piece, right?
Yep.
It's probably hard to see in this picture. There's a little black dot right under the edge of my mouse pointer there, and that's the brake release button. So if you e-stop the robot, there is no brake on joint 1 or 2 of the robot, but there is of course a brake on joint 3, the Z. So if you need to move the robot around, you could just e-stop it and move it around and then hit the brake release and move the Z up and down if you wish. Similarly, for the Hornet or for the Quattro robot, there's a brake release button on the robot, and you can use those brake release buttons if you wish. For the Viper robot, we actually have a brake release box, which is something that you plug into the amplifier, and it only allows you to free up one joint at a time. Again, that's just a safety thing. We want to make sure that you really, really, really want to do it. I mean, the brake release button, it's basically a button and a switch, right? To select which joints you're going to free up. But it forces you to be very explicit and go get the button box and plug it in and dial it to the joint you want and then hit the button. And if you do all that and you still make a mistake, well, we tried.
Was this
Is that all?
pretty
Oh, go
helpful
ahead,
to
sorry.
everybody?
Yeah.
Yeah. I guess I have one other question that I can think of right now.
Sure.
So the application that I'm currently working on is with a Viper 650, and there'll be a gripper on the end of the arm.
Uh-huh.
So I assume that those will just be more bits in the program that will, that I can control with the PLC to open and close the gripper.
Yeah. So generally, I mean, there's digital I/O that comes with the robot, but frankly, in my experience, most people end up just using the digital I/O from the PLC to control gripper I/O because you're already doing you're going to have wiring going to your PLC anyway. It's available. You certainly can use it. It's there for you to use. But I just have historically seen people do more of the like gripper control and those types of things with their
Hardware.
the I/O that's inherent in the PLC.
Okay. No, that makes sense.
So as I, in setting this up, as I indicated to V from Youngblood, Mark and I have been doing this for many, many years, and we find that this is usually a phenomenal starting point that we never really see people needing more, other than maybe a question here or there. But we don't want you to think that we don't want face-to-face either. So it's just, it sounds like both are PLC people, and the concept appears to be, pretty simple. But again, it's better when you, in your case, Brad, you have a system there, so you can actually start playing with it and seeing how it functions. So I know V is working on getting his demo unit up and running to have ePLC as well. So. Anything else?
None.
Huh?
So the valves in there are not pre-wired. The valves, there is an option for a valve pack. So in the Cobra, there's an option you can get for an internal valve pack. And if you use that, you get the kit, you plug it in, and those are pre-wired as signals 3001 and 3002. If, however, you're using the Viper, all the Vipers come with, instead of 2 valves, there's a 3-valve pack in there. But unfortunately, those are not pre-wired, so you actually would consume digital I/O from somewhere. And the manual will tell you how to wire it up, but you actually have to wire up the I/O and power it and everything. Yep. Exactly.
V, P, I thought I had sent that to you, but if I did not, let me know and I can pull it right out of the user manual for the Viper. Okay, either way, just let us know. Brad, Tina, good to go for now?
Yeah, for now.
Yep.
Okay.
Yep. I think so.
Okay. Well, thank you all very much for your time. I'm sure there's some stuff that you'll think of. We'll get off the phone. You'll hang up. Oh man, I should have asked him. Whatever. So if other questions arise, which they always will, certainly please let us know, and we'll do our best to get you answers as quickly as we can.
Yeah.
Awesome.
Thank you very much.
Thank you, everybody.
Thank you all very much.
Thanks, Mark. Okay. Bye.